Well, hello everyone. This is Professor Ma, and this is the introductions on the sections on chain rules and general partial derivatives. Uh, so these are the two topics. We're going to talk about partial derivative of multivariable functions, and then we're going to talk about how do we do the chain rules when we compose multivariable function with another multivariable function with another, so on, so on. How do we keep track of the variables? Multivariable functions, when we take the derivatives, we have partial derivative with respect every one of the variables. So if I want to take the derivative of the variable xi, I treat all the other variables as constants. So for example, if I have the functions defined with the variable vwxy and then partial x, you will treat vwy, the other three, as numbers, and so on and so on. Here's an example. Here's the four variable functions in the vwxy, and with the partial respect to w, the first one over here, okay. And then this will be 0 because that's a constant term. The only relevant one is this one, including wq. So you can check this is the chain give us these different partial derivatives. Okay. Now next is that we can have compositions of multivariable functions, and I can have, for instance, well, before we talk about that, let's talk about a chain rule a little bit. So the example of a chain rule. For example, I have a function in xy that x and y is a function in t. So I can plug in the t into the original z, that I get a function z directly in terms of t. And I want the derivative of the z in terms of the t. And that this is the chain rule for that. And this is basically the total differentials. Okay. Remember, we have the total differential of z is equal to the L, which is partial x, times dx plus m, partial f partial y, and dy, and the gradient dotted with the dx dy, the differential dx dy. But if the differential itself is of things in t, and then this is in place of that, dy dt. Okay, as in change in t, in terms of t. So then I have these replacements. So for example, if this is a function in xy and x is in cosine squared t, y is t squared, I can calculate it two ways. The first way is I put a cosine squared t, and for x and t squared for y, everything in t, and calculate the derivative. That here I introduce the chain rules and product rules, and I get this as the derivative. Or I can do it this way, which actually is taking dz dt's. Okay. I can do it in the formula fashions, and then you wind up, you find out you compute the same things. Okay. So this is just a demonstrations of the chain rules with one variables from xy to t, and take the derivative of z directly with t. Now, in general, you can think of all this composition, and here x might be instead of a function in t might be a function in s and t, and then s and t might be a function in UVW, and UVW might be a function in something else, and so on and so on. How do we keep track of the variable, and how do we take partial derivatives, with respect to the end result? Well, we need a variable tree, and this is how we track multivariable compositions. This is how we keep track of the variable with a tree. It's like a relation whose offspring is who's dependent on whom, like this family tree, sort of. Here's an example. Suppose z is in x, y, x is in s, and y is in s and t. Okay, and then s itself is in u and v, and t itself only in u. Okay. So, and here's then the variable tree that expresses the condition z is in x, y, and that's this, and the x is in terms of s, and y is in terms of s and t, and so on and so on. Okay, so I can just follow the relationship and draw this tree. And this is called a variable tree. The purpose of this tree is to keep track of the variables, who's the input, who's the output at each stage. Okay, and then let's name the things. In general, in mathematics, when we have a tree structures like this, this is called a root, and then this sometimes called a fruit, or sometimes called the leaves. Okay, and so we use these to compute partial derivatives. Okay, so the chain rule. Okay, and let me just do examples. Okay, here's the chain rules. For examples, in this example, z is a formulas in like the last one in x, y, x is in s, s is in v, and x is in s is in u and v, and t is in u. Okay, that was the condition from before. Now, if I want to take the derivatives of this formula with respect to u. Okay, so this is a tree. I want to take partial the partial respect to u, so of z, the root respect to the leaf u. So, and here are the three u's. So first things, I find all the path that leads to the u. We single those out. Then we label each path with the appropriate derivative, partial derivative or regular derivative, partial x, partial. So for example, the first path was here. That will be partial x plus x respect to s, s respect to u. That's the first leaf. Okay, and then we'll add all the leaves together. Okay, so this is the first, second, and third, going to the three paths, and these are all the derivatives along each leaf. All the branch lead to the leaves, and the chain rule says multiply those, and that actually is a differential, three-part differential, that each differential can be broken down into smaller differentials using chain rule, and to keep track of those differentials through this tree. Okay, and then okay, so we can check the partial z, partial v is going down to the other one, then it's going to be this one, and it comes out to be two of these. This is that one, this is that, this is this one. Okay, and here's an example for the end result. Of course, you get the answers in u's and v and x and y, and depends on what the requirement is. You might want to express everything in u and v, then you have to replace the s and x and y by the v. But those just are tedious words. Okay. one interesting thing about this chain rule. Okay, from this chain rule, we actually get a simpler ways to calculate the implicit differentiations in x and y. You know, you remember in 265 we have problems like the e to the xy plus the y squared. I'm just making something, you know, horrible, you know, something real messy times times 1 and divided by y equal to 0. Okay, and that's an implicit equation, and the question is what's dy dx. Okay, and that was a lot of you can do this by implicit differentiation step by step using chain rules, quotient rule, product rule with x and y's in them, and then solve for the dy dx. And that actually kind of lengthy to do. And here's an easy way to do. The equation, let's move the equation xy to all to one side. I take the partial derivative with respect to impulse functions. We'll take the partial using the chain rule, okay, respect to x. Y to respect to x, because we want dy dx, the end result x. So if we do it that way, and treating y as a function in x, okay, and then I get this equation, dx dx of course is 1, and this is the power I want, so I can solve dy dx and wind up with these equations. And in other words, dy dx is the negative of the partial x divided by partial y. And that's a lot shorter calculations. I didn't have to do all the chain rules, and the 265 method might be a lot longer. And here's an example. Okay, and the dy dx can be calculated easily. So here's the partial derivative and put them together into fractions, and that's dy dx. Okay, that's it. Okay, see you next time. Bye bye.